Greetings, everyone. Welcome to the MorteSense DIY home security system.
I'm Shohin. I like to dive into the intricacies of backend technologies.
My name is Diego. I worked on the documentation and on the hardware in this project, and I'm interested in human-computer interaction.
Hello everyone, I'm Pio Garcia Carrasco. I play the role as a front-end engineer. During the project, I'm currently an AWS cloud engineer.
Hello, my name is Spartak Gevorkian. I worked as a hardware engineer for the project, and my full-time job is an R&D engineer at ANSYS.
All right. So moving on, we're going to be talking about some of the keystone studies that helped inform this project, the development journey that we went on during the course of 2023, some of the work that we did after we submitted the paper to this conference, as well as some future threads of work going forward after the conference. So starting off with the literature survey, the current market has hardware and software ecosystems made by the folks over at Ring, Blink, Wise, and SimpliSafe. These tailored systems are typically made for businesses, so they're less so for an individual living inside of a house by themselves or with their family. They're more so for small-scale businesses using network-attached storage as well as just custom hardware that implement and program themselves that they have only their understanding of it. So some of the technologies used in these ecosystems would include the passive infrared motion sensing, light-dependent potentiometer sensors, as well as proprietary microcontrollers. This refers to the PCBs that are made by the folks over at Ring, Blink, etc. And the activity modules refer to modules that can detect when a door is opened, when motion is detected, when glass is broken, and when gas leaks are detected. Moving on, we have the different avenues of development and research. We have different sensing technologies, including microwave motion sensing or Hall effect sensing. We have the different microcontroller platforms, which include Atmega, Raspberry Pi, and Arduino. And then we have energy delivery, which is different forms of household batteries or batteries that are designed and then fabricated. And then on the firmware and software side, we have Internet of Things, blockchain, but the most interesting one is machine learning because there's been a trend in recent research where we are focused on giving more detailed analytics, but I'll talk about that during one of our keystone studies. And then in terms of wireless communications, we have Bluetooth, GSM, SMS, and web-based messaging APIs. So moving on to our first keystone study, this is Hossein Malekian back in 2017. This particular study explored the vulnerabilities that exist in DIY home security systems that use sensors and microcontrollers. They used the Raspberry Pi platform and Zigbee communications to make a design capable of detecting motion, door activities, and fire/chemical leaks. This particular study gave us a frame of reference in terms of possible vulnerabilities that the system could have and allowed us to understand some of the possible challenges that we should anticipate when designing the system. We were interested in using 802.11 Wi-Fi as well as some possible Bluetooth when experimenting with different platforms and sensors based on our understanding of this study. Going forward in Sarhan 2020, this was a very comprehensive literature review that provided an overview of dozens of reports. And this particular study was quite detailed. It served to us as a basis for which to search for the different sorts of studies that explored different means of securing the household. It's the keystone paper in our understanding of the state of the art, which leaves more recent research to understand recent developments in sensing technologies, as well as modern sustainability practices. So, going past the point at which this paper was published, research experienced something of a turning point with platforms and technologies having a focus on the Internet of Things and deep learning, as opposed to creating ecosystems with different means of securing a household. So there's a bit more of an emphasis on detailed analytics as opposed to live prevention or rapid response. So going on to our third keystone study, Wayuni et al. In 2021, this was a passive infrared based system that's capable of notifying the user within 21 seconds whether the end user was located about 100 kilometers or more away from the site using web messaging protocols. They used the Wemos D1 microcontroller as well as the Telegram API to be able to accomplish this. So the initial notification was within that time, but the system is capable of continuously notifying the end user immediately at the site where there was detected activity. So there were some shortcomings of this study in terms of language barriers, but the usage of web messaging inspired us to consider including web messaging in addition to the SMS notifications we initially set out to use with the Twilio API. We'll talk about that a bit more in the development journey. So the group is exploring integrating the Telegram API, but that's going to be also explored over in comments and future work. So I'll be handing it off to Spartak.
Hi, I'm going to talk about the development journey. So during the development journey, we established solid goals for our hardware and software. For the hardware, as mentioned before, we wanted to use the newest microwave motion detection technologies, as it allows to detect motion even through semi-transparent objects, so you cannot hide behind a piece of cloth. Additionally, we required at least 10 meters of efficient range. As we were creating an open source ecosystem, we also wanted our modules to be easily added and removed by the end user. This allows users to customize product according to their needs. And for the software goals, we wanted to have light firmware capable of conserving energy. In other words, we wanted long battery life. Software also had to include basic groundwork for the features such as analytics, notifications, and be fully customizable. You can add and remove analytics, notification, and everything else. Sustainability impact. So for the energy efficiency, we implemented a sleep mode, which reduces the energy consumption of the device. And our ecosystem also is open source and modular, as mentioned before. And it allows users to remove components that are not required, which helps to reduce the e-waste, also helps to change the size, make it more compact. Draw heavy inspiration from the framework laptop, advocated efforts by Louis Rosman. We provided open documentation for the end user to access the schematics and perform maintenance repairs independently from us. So here's the hardware design. We decided to go with Raspberry Pi Pico W because it's very compact and has a 2.4 gigahertz Wi-Fi module, and power consumption is very low. You only require 5 volts of power to work with it. And power delivery is flexible. So we explored different options like 9 volt and seed batteries, but we favored the 9 volts for rapid prototyping. The device also can work using 2 AA batteries. And for the motion sensor, we use 5.8 gigahertz microwave motion sensor, which relies on the Doppler effect to capture motion data. We also provide PCB diagram. It's open source and user can have access to it. And we use freezing program to design and simulate those freezing files are also available and they are published. Firmware was written in MicroPython, which was later translated into C for ease of use and implementation in the hardware. And here you can see our first rapid prototype. On the left image, you can see the breadboard prototype in action. So you can see when I move my hand over it, it's going to detect the motion and rapidly send an SMS notification. And on the right, you can see the final soldered prototype. It's very compact and small and lightweighted, and you can place it anywhere you want. I'm going to pass software design to Shohin.
Because our product requires a notification system to keep users informed about updates, events, and other relevant information, we decided to move on with React.js and TypeScript, Flask, Python, Tailwind CSS, Git, MySQL, and AWS Stack, and Discord for Agile. The system facilitates several key actions: registration, client-device connection, alert subscription, and alert reception. Each action serves as a specific purpose within the system's functionality. The registration allows users or devices to establish their identity with the system. Client-device connection enables communication between the devices and the system. And alert subscription allows users or devices to specify their preferences for receiving alerts. And alert reception involves the system notifying subscribed users or devices about relevant events. In the sequence diagram, these actions are depicted as a series of steps or interactions between different components or objects within the system. Each action leads to the next, and showing the flow of activity within the system. The outcome of these actions is that the system becomes capable of effectively managing user or device interactions. Users can register and receive alerts based on their preferences, while devices can establish connections and receive necessary updates from the system. In the development of our system, we faced the challenge of integrating hardware and software components while prioritizing energy conservation and performance optimization. To address this, we utilized FreeSync for virtual simulations, enabling us to refine hardware designs and identify compromises necessary for energy conservation. Concurrently, we use JMeter for comprehensive software testing, including performance, functional, and load testing, ensuring the reliability of our system under various conditions. Additionally, we implemented efficient database transmission strategies to optimize data exchange and enhance system operation. As a result of these efforts, we successfully validated hardware designs through real-world testing, enhanced system and reliability, and optimized data transmission for efficient operation, thereby achieving our objectives effectively. We achieved a functional hardware configuration, but encountered challenges in its maintenance. Notably, the motion sensing module successfully detects and records motion up to 30 meters, and enabling rapid user notifications within 3 seconds of detection. However, remote collaboration posed difficulties, particularly in reporting and analytics, due to the distinct responsibilities between hardware and software teams. Moreover, legal complications related to the Twilio API necessitated a switch to an alternative messaging API. Additionally, the creation of boilerplate templates for diverse tools and services aimed to reduce dependencies and legal risks. Let me start with the current and future work. Our open source repository stimulates responsibilities with MortEdge focusing on front-end, MortForge handling the backend, and MortDocs managing documentation, MortCraft overseeing firmware development, and MortAwesome serving as the landing repository. This structured approach ensured clear delineation of tasks and responsibilities across different aspects of the system, facilitating efficient collaboration and progress tracking throughout the development lifecycle. In our ongoing effort, we have already created a CAD model for the microcontroller. Now our focus is on developing a model for the microwave motion sensor, which will facilitate virtual assembly modeling before any fabrication takes place. Perhaps look for common wires and assets on open source CAD file hosting websites like GrabCAD and Thingiverse. Our team did a great job creating boilerplate code by making different kinds of templates, improving tools and APIs for different teams to use together, and smoothly adding new technologies to our system. We also focused on making customized solutions to fit each end user's needs and made our system flexible so it can adapt easily. Plus, we found that using different fields of expertise together helped us make our services and tools work for more things. Making it easier to solve tricky problems, the overall approach made sure our solutions could grow and work in lots of different situations and do what end users needed them to do. I'll go ahead and hand it over to Diego.
Hello, everyone. Now I provide you with an overview of the future plans for the project. Looking ahead, we plan to enhance the system hardware and software components. In terms of hardware, we plan to develop 3D printed enclosures for added protection, support new microcontroller platforms for greater system versatility, and also integrate additional sensors and modules for expanded functionality of the project. On the software front, we'll explore advanced tools for more detailed analytics and also provide support for various notification methods catering to both in-person and remote monitoring needs of the system. Our commitment to user empowerment also extends on our future documentation efforts as well. We plan to create comprehensive facts and troubleshooting guides to address common hardware issues, ensuring that users can easily diagnose and fix problems when setting up the system. Additionally, we'll leverage GitHub issues to document software challenges and provide timely updates and revisions, fostering a supportive community around the project. We're also excited to further develop the documentation, as I explained it on the previous slide. So we'll be including detailed guides for using templates. And also in the spirit of innovation, we're considering leveraging existing documentation to create a data set for a possible AI-based assistant chatbot, with the finality to help users with the establishment and maintenance of the system and deployment. In conclusion, our project stands out for its affordability, accessibility, and commitment to sustainability. We've designed a modular system that's easy to maintain and expand, reducing electronic waste and supporting circular economy. Through comprehensive documentation and transparent practice, we aim to empower users and promote sustainability in the realm of home security system. We'd like to extend our heartfelt thanks to the San Jose State University Charles Davidson College of Engineering, our mentors, Professor Paramas Mortesaye and Mahima Gumbe Suraj, and of course, the Martin Luther King Jr.'s Library Student Computing Services. Lastly, here are the references that guide our research and development. We extend our thanks to these sources for their valuable insights. For more details, please refer to the list. Thank you everyone for your attention. We invite everyone to explore our project further on GitHub at github.com/MorteSense. And if you have any questions, please feel free to reach out to us. Now we love to hear your thoughts and answer any questions you may have. Let's open the floor for discussion.